Hello, hello. So we're going to continue talking about inference with means when we're dealing with two samples or doing some kind of comparison. But we're going to specifically look at what happens when our data from our two samples is not independent. So again, remember our steps, nothing new, same steps as always. But I wanted to put those up there. So what if the two samples are not independent? So when two samples are not independent, we may still be able to do the inference procedure in a different way using what we call a paired t-test or t-interval. So I'm going to go show you some examples and ask you this question: which situation requires an independent two-sample t-procedure and which requires a paired? So again, independent would mean the two groups are completely separate. Paired means that there's a connection between the two groups. So researcher wishes to determine whether listening to music affects students' performance on a memory test. In example A, he randomly selects 50 students, has each student perform a memory test once while listening to music and once without listening to music, and then compares the two scores for each student. In scenario B, he randomly selects 50 students, has half of them perform a memory test without listening to music, and the other half perform the test while listening to music. He obtains the means and standard deviations for both groups and then compares them. So if I think about, where both of them have technically two groups of scores, both of them are dealing with two samples, but in A, the two sets of scores are coming from the same students. So it's paired because we technically have two groups of scores, but they are connected because the same student does both tests. So we have technically one group of students and two sets of scores. In B, we have different students doing different things. So we have 25 sets of scores, 25 scores from students doing the test without listening to music, and 25 with listening to music. So that would be an independent or two sample procedure. So another example, a manufacturer has designed athletic footwear, which it hopes will improve the performance of athletes running the 100-meter sprint. In scenario A, 30 are selected. One group of 15 runs the sprint wearing the new footwear, and the other group of 15 does their normal footwear. In scenario B, 30 athletes are selected, and each of them runs one sprint wearing the new and one wearing their normal. Randomization determines which one they run with first, right? So this one, in scenario A, we have two separate groups who are doing two separate things. So those two sets of numbers aren't going to be connected because they're done by different people. Whereas with scenario B, we have 30 sets of numbers and they're done by the same person. So we have kind of pairs of data. So it is paired. So now we're going to look at how we actually perform the test or the interval. So some tips on deciding paired versus independent. For paired samples, the data always has to be the exact same number of elements because the whole point is that they are pairing together sets of numbers. Two sample procedures, the two sets of data can be different sizes. So be careful here. Two sample can have the same number of elements in each sample. That is possible. So just because it's the same number in each setting doesn't mean it has to be paired. It could still be two sample. But if they're different sizes, we know it has to be two sample. It can't be paired. So it's kind of like helps us one way, but not necessarily all the ways. Look at, are the pairs of numbers linked somehow? So can I take one value from one list and specifically link it or pair it with one value in the other list? And that could be because it's the same person, but it could also be maybe these two sets of numbers are coming from like twins or a married couple, or they both come from data from the same country. Something like that that would maybe link one number from one list to one number on the other list. That would indicate dependence, so a paired procedure is needed. Does the problem indicate that the two sets of data were taken separately? So separate is a good clue that we're doing something that is independent. When possible, a paired T procedure is always a better option. So just in the real world, when we're designing experiments, um, it's always going to be a better option, just numerically, mathematically, it's going to give us better evidence if we can do a paired. But why is that true? So here's a list of data where we have students who took maybe like an SAT, this maybe be SAT math scores or something, maybe before a prep class and then after. So we can see their two sets of scores. If I do it as a two sample procedure, what's going to happen is that my before scores, if I look at those, the standard deviation of those before scores is 73.04. The standard deviation of our after scores is 136.05. So when we do a two sample procedure, both of those standard deviations are kind of combining and they're both part of the problem. So there's a lot of variation happening when we deal with it as a two sample because we have variation in the before scores and variation in the after scores. Whereas if I look at it as an improvement, if I think, okay, this is the same student, so instead of looking at it as two different numbers, why don't I just look at it as how much did they improve? So if I'm looking at it as an improvement in scores, those difference numbers, the standard deviation of the differences is really small. It's only 15. So all of a sudden we have way less variation in our data than we did when we did it as a two sample. Less variation means more exact answers. It means our intervals are going to be narrower. It means that our t-test is going to be probably more accurate and more usually smaller p-values that give us better evidence. So if we can do a paired procedure with a experiment, it's always going to be a better option. Right? Our conditions for paired inference are mostly the same. So do we have a random sample or representative sample? They're not independent samples. That's the whole point. That's why we're doing it as paired. It's because they're not independent. So be careful. Just because there's two groups of data, right? Don't say that they're independent like you would with a two sample procedure because they're not. Um, yeah. 10% condition still applies unless it's like a full-on experiment where they clearly took volunteers. But it's always okay to put 10%. And then normality, we are just checking normality for that group of differences. So again, there are three ways to check normality. So one would be, is the population of differences in numbers normally distributed? That would be given, which it rarely is. Second, is our sample size large enough? So again, we're technically dealing with one sample, just kind of two sets of data. So there's that one sample size bigger than 30, or graph the differences, the sample differences, and check for skew and outliers. All right, so that would be our conditions. Okay, so let's finally get to an example. So this example is talking about baseball or softball. Can students throw a baseball farther than a softball? Researchers conducted a study involving 15 randomly selected students from a large high school. After warming up, each student threw a baseball as far as he or she could and threw a softball as far as he or she could in a random order. So the random order is just telling us that they randomized whether they would throw the baseball or the softball first for each student. So maybe they flipped a coin to determine which they would throw with first. That's important because obviously if you're throwing two balls in a row, it's possible that you might be more tired after the second one, or you might be more warmed up for the second one and throw better. Hopefully they rested in between, or maybe they did it on separate days, but either way, that randomization just gives us a better idea that we are dealing with good data. So the distance in yards for each throw is recorded. Here is the data. So the first thing we would do once we determine we're dealing with paired data is that we're going to go ahead and find the differences. So in this one, I'm going to do baseball minus softball. You could do it the other way around. You just want to make sure that you are being clear and keeping track of which way you subtracted and that you're doing it the same for each student or for each set of data. So I'm going to go through these and I'm going to subtract each of them. So 65 minus 57 is 8. 90 minus 75 is 15, etc. So if I go through and subtract the two numbers for each student, that is giving me my differences. So now for the whole rest of the problem, I only care about this set of numbers. I'm not going to use the rest of these numbers at all, so I can essentially just kind of cross them out in my mind. I only am dealing with these differences. So we're going to go through our steps. Our first step is to define our parameter. Now my parameter is technically just one parameter of the differences. So I'm going to write that as mu diff, or you could write mu d, is the mean difference in distances balls can be thrown by students, baseball minus softball. Again, we want to make it super clear in as many places as possible which way we're dealing with, which way we're subtracting. That just makes sure that you know it for when we write our conclusion, and also that whoever's grading your question knows which way you subtracted. So that would be my parameter, the mean difference in distances balls can be thrown by students, baseball minus softball. So our conditions, our first condition, do we have a random sample? It does say that they randomly selected students. It also tells us the random order of balls thrown, which is also helpful. One note I will make is that sometimes with a paired t-test or t-interval, we are dealing with a experiment. And so sometimes with experiment, it's not a random sample, it's volunteers. So a couple ways you could deal with that is you could say we assume this group of people is representative of the entire population. That's a good way to get around that. Or you can just say, hey, it's not a random sample, which means I can't generalize my results to a larger population, but we're still going to do the test. So those are a couple of ways you can kind of deal with that issue if it's not a random sample. But if there's a randomized order of something, that's always good to note because that's kind of going to make sure our data is a little bit more believable. 10%, I'm not going to worry about too much, but we would need to do our third condition, which is about normality. So I wasn't told the population is normal. My sample size is only 15, which is not big enough. So what I would need to do is graph a graph of the sample data. And the sample data we're graphing is the differences. So hold on a second. I'm going to go into my calculator and put in my data. So I put the data in, and one thing I wanted to show you just as an extra option, I went ahead and put in the two sets of data. So I put the baseball scores under L1, and then I put the softball scores under L2. So one thing that I could do is I could go to L3, I can go up to highlight L3, and then I'm going to put second 1 for L1 minus second 2 for L2 and then push enter. And then now very quickly, I have all the differences in L3. Oops. So that's one way that we can handle the differences. If you have a really long list or if it's numbers that are kind of hard to subtract quickly, that might be something you want to do just so that you don't have to do some of that math firsthand on paper. That does mean you have to type more numbers in the calculator, but for some people that trade-off is worth it so they don't have to do all that mental math. Again, you could also just write the numbers down on your paper and then copy them into your calculator. It doesn't matter how they get in there. The only numbers we really care about are those differences. So once I've done this with L3, I'm only going to use L3. So I'm not really even caring about L1 and L2, but that is an option. So I wanted to throw that out there. So once I have the data in, again, I could do a quick graph in my calculator by going to second y equals. I'm going to turn on my stat plot if it's not already on, make sure histogram is chosen. I'm going to change my X list to L3 since that's where my differences are. If you just typed them in L1, you would leave it as L1. Now I have that, and then I'm going to do zoom 9 for zoom stat, and then there's my graph of differences. Again, I noticed maybe a tiny bit of skew, but nothing major, and definitely no outliers, so we are very safe to use a normal model for our paired procedure. So now we're going to get to the questions. So I basically wanted to do this one example for both a um, hypothesis test and a confidence interval, just to kind of speed up the process. So on part A, it says, is there evidence at the alpha 0.01 significance level that students on average can throw a baseball farther than a softball? So we've already defined our parameter and we've already done our conditions. The only thing that's extra for a hypothesis test would be to write our hypothesis statements. So the way we would write that, since our parameter was mu diff or mu d, it was the difference. My hypothesis statements look a little bit different than they would for a two sample. So my null hypothesis for a two sample and for paired is that there's no difference, that there's no difference between the two groups of numbers. So the way I write that for a paired is to write mu diff equals 0, meaning that the difference between the two means is equal to 0. Our alternate is going to be either mu diff greater than, less than, or not equal to 0, depending on what the question. So if we're wanting to show that students on average can throw a baseball farther, then we think that the baseball number is bigger. So since I subtracted baseball minus softball, I want that difference to be positive, or that's what I'm trying to show. So I chose greater than 0. If you had subtracted the other way, if you had subtracted softball minus baseball, then to do this same test, you would say mu diff less than 0, because that would mean that the softball number was less than the baseball number. So you have to make sure that your alternate hypothesis matches the way that you subtracted when you did your data. So those are my hypothesis statements for that first step. We already did conditions. So now we're ready to do the math, which will be really nice and easy since I've put my data in my calculator. So I'm going to go ahead and do stat tests. I'm going to choose t-test. So remember before, this is what we use for one sample t-test, but it's also what we use for a paired t-test. Essentially, a paired t-procedure is just a one sample with the differences. So we're kind of just doing it as a one sample t-test, but we're going to use the differences. So t-test is what I'm using. I'm going to choose data because I have my data in the lists. My null hypothesis, mu0, would be 0 because my null is that there's no difference. My list, mine was in L3. If yours was in L1, just keep it as L1. And then I'm trying to show that that difference is greater than 0, so I'm going to choose greater than. And then I'm going to choose calculate or draw, whichever you like better. I'll choose calculate this time. And we get our t-score and our p-value. We also are given the mean x-bar. We also are given the standard deviation. So in terms of actually writing out the formula, that would be helpful, right? But I can just write it out like this. So a paired t-test, t is 3.85, p-value is 8.8, e negative 4 means times 10 to the negative fourth. So it's actually very, very small. We move that decimal place over to the left 4 times. I think I put too many zeros there, but it should be 0.00088, or 8.8 times 10 to the negative fourth, which is very, very small. We also want to make sure and write down our degrees of freedom. 14 and minus 1, same degrees of freedom as for a one sample since it's essentially just a one sample procedure. Then we write our conclusion. Since our p-value is less than, very less than alpha of 0.01, we reject the null. We have evidence of our alternate that students can throw baseballs farther than softballs on average, or that the baseball distance is on average bigger than the softball difference, however you want to say that. Again, that conclusion should have the word mean or average in it somewhere since we're talking about an average and not like individual numbers. If we were doing a confidence interval, so this is a 98% confidence interval, we already did our parameter and then our conditions. We would call this a paired t-interval for a mean difference, which is what I'm going to put there. Usually we would put that at the top of step 2 with conditions, but I'm just going to put it here. And then we're going to do our interval. So I'm going to go straight to my calculator. I'm going to do stat test t interval. So again, a paired t interval is really just a one sample t interval for the differences. I'm using data. My data was in L3, which is the differences. And then my C level is 0.98. And calculate, oops, try that again. I accidentally pushed enter too many times. There we go. And then we get our interval. So 2.17 to 11.43. Again, we're given that mean standard deviation. So if we wanted to write out the formula, we could. It's the same formula as for a one sample, since it's basically a one sample. So there's my interval. And then when we interpret it, remember we're interpreting our parameter. It's basically the difference or the average difference in baseball and softball scores. So the way that I say that could look a couple different ways. I said we're 98% confident that students can throw baseballs between 2.17 yards and 11.43 yards farther on average than they can throw softballs. We could also say we're 98% confident that the mean difference, baseball minus softball, in distances a ball can be thrown is between 2.17 and 11.43. That would work as well. So either way, that is my conclusion. So that is it for this lesson. Very similar to stuff we've already done. A paired procedure is basically just a one sample procedure using the differences. And that's all you need to know. All right, y'all, have a good day. I'll see y'all next class.